Welcome. In today's lecture, we're going to look at a sorting problem, in particular insertion sort, and the focus will be actually on proving that insertion sort is correct. So we're going to see loop invariant proofs. So this lecture also serves as an introduction to loop invariant proofs by the example of insertion sort. But let's start with the sorting problem. So in the sorting problem, we have given a sequence of numbers, and yeah, we want to sort them. So this is our input, and the output should be the sequence sorted, or more formally, a permutation of this sequence, such that the smallest the first element is smaller or equal to the second one, and so on. So that's the output that our algorithm should produce. When talking about the sorting problem, we are not concerned about how these numbers are represented. So we will simply assume we can compare two numbers in constant time, and you will use that in the sorting algorithm. Chances are you probably already know quite a few sorting algorithms, or maybe not. Maybe this is the first one. Yeah, so you might know selection sort, merge sort, heap sort, quick sort. All of these algorithms will feature in this course sooner or later, and probably you know even more sorting algorithms. But today is about insertion sort, and even if you know it, since we are going to look at the correctness, so if you haven't seen the correctness proof for insertion sort yet, this lecture will have something interesting for you. Okay, so the intuitive idea behind insertion sort is nicely explained using playing cards. So assume I have cards, and now I pick them up one by one with my left hand, and every time, or no, I hold them in the left hand. I pick them up with the right hand. Every time I pick up a number, I go through the cards on the left hand and then position it on the right spot. And because in this, before picking up a new card, this sequence is sorted, then when I place a new card in the right position, then again I have a sorted sequence. So this already is a loop invariant, and this will be feature later, I mean a more formal description of this in the proof that we're going to do. Okay, insertion sort is an example of an incremental algorithm, and in this course we're also talking about how to design algorithms. So I want to look at this take a step back and see the principle behind insertion sort. So it's an incremental algorithm. And incremental algorithms work as follows. If I have an array as input, I essentially just take the elements one by one and make sure that I have solved the solution for the problem for the elements that I've seen so far. So this can look as follows. So we first compute a solution for the first element, and then we have a loop over the remaining elements. And in this loop, we compute, in the jth iteration, we compute the solution for the first j elements, so the elements in this array from 1 to j, but based on the solution of the first j minus 1 elements. And then at the end, we return the solution for the full array. So a very simple example of this is, I have an array, I want to find the maximum. Okay, I first take the first element, take that as a maximum, and then I scan the array. Each time I see a new element, I compare it to my current maximum, and if it's larger, I set that to the maximum. I mean, this is a very simple incremental algorithm which exactly follows this idea of I compute a solution for the first j elements based on my solution of the first j minus 1. This is the maximum computed so far, plus a new element. But we are not looking for a maximum, we are sorting. Okay, so how does this look like for the sorting problem? So the solution for the first element, okay, if I only have one element, it's simply sorted, I don't have to do anything. Now in each further iteration, I need to insert the jth element into the sorted sequence of the first j minus 1 elements. Okay, and how can we do this? Okay, insertion sort does this in the following way. So for the first element, we had to do nothing. So we immediately start with the second, with this loop. And this now works as follows. We take our new element, we call that key. We compare key to the last element in the sorted sequence so far, which is, because it's the last element, the largest element. And if the last element is larger, I will move it by one position. So I will point initially to j minus 1, so that's the last element of the array so far. So and while I'm not at the beginning of the array and I see an element that is larger than the key that I want to insert, I move that element forward by 1, meaning I set ai plus 1 to the value of that element. So now I have a space on position ai. I decrease I by 1 and do the same with the element before that, and so on, until I find an element that is not larger. And then I have a free spot to insert my new element. And that's exactly what I do. Here's also a short demo. Go there. Here, so let me just first start playing it and then interrupt it somewhere. Okay, so my current key, you see here. I compare it to the element before that. It's larger, so I'm going to shift that element by 1. Now, okay, I still see a copy of it here, but that spot, what is now red, is free. Now I compare my key to the element before that. That one is smaller. Let me do this. Now I is this red one here. This is smaller. Now I insert the key just behind that one, and that is the spot that I made free by moving the blue one here. Yeah, and that continues until the array is sorted, or until we want to continue with this lecture. There's also Python code in the lecture slides, so this is just for you to play around. So you don't need to know Python for this course, but if you know Python, or if you want to get to know Python, or if you simply appreciate Python because it's very readable, you have it here. You can evaluate whatever you have here. So you can play around with the algorithm in a nice way with these slides. Okay, so are we done? Obviously not. I mean, I already emphasized that correctness and efficiency is important to us. So we are only really getting started now. So what we want to know about an algorithm always is it correct? And how efficient is it? How efficient it is mainly, or first of all, the running time, but we might also ask questions about memory, for instance, or other relevant aspects of the algorithm. Yeah, but the core is really correctness and running time. And today what we're going to do is correctness. Yeah, so if we have an algorithm, we should always also prove that it's correct. Maybe for insertion sort, you think, okay, obviously it's correct, but A, maybe it's not quite as obvious, I would say. And B, the more complex the algorithms get, the more difficult it will be to see that they are correct, and more easily you might actually think it's correct and it doesn't work. So it's really important to check correctness, and checking means proving. We will be looking at various techniques. We will see different techniques to prove correctness of algorithms, but today we're going to see loop invariant proofs. So loop invariant proofs are used to prove the correctness of algorithms that include a loop, in particular incremental algorithms. So a loop invariant is simply a statement or assumption for which we prove that it holds at the start of every iteration of the loop. So I already mentioned at the very beginning with insertion sort, essentially our loop invariant is that the numbers that we've seen so far, that those are already sorted. We will have to do this a bit more formally, but that's our loop invariant for which we then want to prove that it shows that it holds all the time. Okay, a loop invariant proof always follows a specific structure, so it always has 3 components, and this is initialization, maintenance, and termination. So initialization says the loop invariant should hold at the very beginning. So when I step into the loop for the first time, so at the beginning of the first iteration, the loop invariant should hold. Maintenance says that if the loop invariant was true at the beginning of an iteration and I now run through the loop, then after that iteration, the loop invariant is again true. And those two together show the correctness of the loop invariant, because if it was true initially and every time I run through the loop it stays true, and then it also is true at the end. And at the end, that's now what we do when we talk about termination. So, I mean, formally, if it's not clear that a loop would terminate, then checking termination might be part of it, but termination really refers not to proving correctness of the loop invariant, but using the loop invariant after the loop has finished to prove something useful about the algorithm, in our case, to prove the correctness of the algorithm based on the loop invariant. We'll see that by the example of insertion sort next, then it also will be clearer. Okay, so here's insertion sort. And our loop invariant will be, I talked about it already a couple of times, but now this is kind of a more formal statement. As a loop invariant, what I want to have, click here, as a loop invariant, what I want to have, I want it for a laser pointer in particular, is that the array A1 to j minus 1 at the beginning of the iteration j contains the same elements as at the start of the algorithm, but now sorted. Yeah, so the complete loop invariant would state at the beginning of iteration j, and then what it says here. This is a loop invariant for which we now want to do a loop invariant proof. So we need to do those three steps: initialization, maintenance, termination. So initialization means we have to start check whether this statement is true at the beginning of the first iteration. At the beginning of the first iteration, j is 2. Yeah, j is 2, meaning that this a1 to j minus 1, which shows up in the loop invariant, is simply, so j minus 1 is 2 minus 1 is 1. So we're essentially just saying a from 1 to 1, so simply the first element should contain the element that was initially at that position in sorted order. Okay, we didn't change anything yet, so the same element is still there, and as a single element, it's also always sorted. So check. Maintenance. So for maintenance, we want to show that if the invariant holds for the jth iteration at the beginning of the jth iteration, it then also holds for at the beginning of the j plus first iteration. Okay, so if it holds at the beginning of the jth iteration, it means that the array from 1 to j minus 1 is already sorted. If you now look at what insertion sort does, okay, so I go through the previous elements, of which I know by the loop invariant that they're already sorted. I find the position where for the first time I see a small element. All elements behind that I shift by 1, place a new element there. So given that the previously from a to 1 to j minus 1, the array was sorted, now this means that the smaller numbers will be before in front of the position where I now inserted the element, still in sorted order because I didn't change that. And the other elements, because I simply shifted them one back, they are also still sorted. And the new element, by construction, is on the correct position in this sorted order. Okay, so this was kind of a bit of a high-level argument about this while loop. Of course, if you want to kind of go into detail, you would also show that this while loop does exactly what I said it does. That's not what we're going to do here. So this is now the maintenance step of the loop invariant proof of insertion sort finished. Now termination. in termination, we make use of the loop invariant to show something useful about the algorithm after the loop has finished. So I use the invariant and I use the condition that the loop finished, so the termination condition. The termination condition is, so if you have a loop, in every step, j is incremented until j is no longer in this range. So until j is above the length of a. Yeah, this is a termination condition. And more specifically, j is then length of a plus 1, because we increment. In the last iteration was the length. Then in the next iteration, which does not happen because we're outside of this range, it would be length plus 1. So this is the j that we have when we step out of the loop. Now, what does this mean for us? So the loop invariant said, so in brief, it said that a1 to j minus 1 is sorted. Yeah, it's same elements and sorted. Now j is this. So if for j I plug in the length of a plus 1. Okay, plus 1 minus 1. This minus 1 plus 1 cancels. So now I'm saying a from 1 to length a. So this is simply equals a. A is sorted. And this means the array is sorted, and this means insertion sort works correctly. Okay, so here's a small quiz. The quiz is as follows. We have linear search. Okay, I should maybe say what linear search should do. Linear search, I have an array, I have one element. If that element is in the array, I should return an index at which this element can be found. It could be several indices. I just want to have one. If the element is not in the array, I want to return null. Here is an algorithm. Here is linear search, which exactly gives me or should give me that output. But to make sure, we should do a loop invariant proof. Now have a look, take your time, have a look at these loop invariants and decide which one works for a loop invariant proof. Okay, let me try. No, the first one directly is correct. So let's see what that was. Okay, so what we have is that at the beginning of the iteration with index I, so this is kind of a typical beginning of a loop invariant. If the answer is a number, an index, so if it's not null, then at that position x can be found. Otherwise, so if answer is null, then x is not in this array seen so far. And you can do this as an exercise. Do your initialization, maintenance, termination, and prove that linear search works correctly. Yeah, I again brought you the Python code for linear search if you want to try it yourself. But now let's move on. So here I have collected some items, some to take into account when making a loop invariant proof. So things that often go wrong, which you should take into consideration. And those are the following. Have you written down the loop invariant? It happens often enough that you start writing down a loop invariant proof without actually having formulated a loop invariant. But obviously a loop invariant proof, proving something about a loop invariant only makes sense if there's a loop invariant. So make sure you have a loop invariant before you start. Then most loop invariants will have to have the property that the loop variable, so I or j, actually shows up in the invariant. Yeah, so if the invariant does not refer to the variable, sometimes in very simple settings that might make sense, but typically there's something wrong with your loop invariant. Okay, then your loop invariant should simply also work with work. So in particular, it should kind of hold at the very beginning that you need to check, not only maintenance, but also initialization. Then it's not enough for the loop invariant to be correct. Obviously, it also has to be strong enough to prove something about the algorithm. So you could have an assumption for which it's easy to prove that it's always correct, but if it doesn't help you at the end, then it's not a good loop invariant. If your algorithm has several loops, then you should do different loop invariants for the different loops, and also make it clear for which loop you're currently doing a loop invariant proof. Then, okay. Often enough, you always have to be careful with I minus 1, I plus 1. This easily goes wrong in a loop invariant proof. Just kind of check your numbers. Typically, if you do this at the beginning for the initialization, if you plug it in, you will see whether your I or I plus 1 is correct. But just be careful about it. In the maintenance step, if in the maintenance step you're not using the loop invariant, then something's wrong. It shouldn't be a loop invariant proof, or most likely your maintenance is simply not quite correct. Yeah, so somewhere in the maintenance you should make use of the loop invariant. So if, for instance, the insertion sort example, if I do the maintenance step and never use that the previous elements were sorted in my argument, then you can be pretty certain, and in the case of insertion sort, certain that my argument is at best incomplete. Also, termination. If in the termination you're not using the loop invariant, something is wrong. The whole purpose was to make use of the loop invariant. So make sure. Your proofs should also always be kind of about the algorithm itself. So here it's also can be quite useful to have pseudocode, and you can make references to specific lines. So make sure you argue about the algorithm and not what you think what the algorithm does. Because what you think what the algorithm does, that's what we're trying to prove. In the termination is not about proving the loop invariant. The termination is really about using the loop invariant to conclude something interesting about the algorithm, most commonly to prove that the algorithm is correct. Yeah, so initialization maintenance proves the loop invariant, termination uses the loop invariant. And also what you should be careful about in the maintenance step, you use the loop invariant of the previous iteration and the current iteration. What does the current iteration do? You should not in your maintenance argument say, refer back to what did the algorithm do in the previous steps. No, all of that should be already captured in the loop invariant. So loop invariant plus the current iteration. That's all to conclude. If you want to know more, have a look into the book. So we're using the introduction to algorithms. You'll find more details about all of this also there. In particular, try to prove loop invariants, go through the examples there, see whether you understand them, see whether you could do them yourself. It's always good if we talk about algorithms, simple algorithms at least, also just implement them yourself. This gives you a better understanding of the algorithm. And since this is the beginning of the course, make sure you engage from the very beginning. These loop invariant proofs, they are already quite formal, but they are important later in the course. So make sure that you stay ahead of the material. Okay, until next time.